So in the last class, we finished the first order system with the closed loop transfer function of y over x, 1 over tau s plus 1, and we named tau as the time constant. So I'm going to work this today also. And for different inputs, we got this table, just refreshing your mind for the error signal, right? That you have in your notes, just refreshing your mind. For the impulse, for the unit step, for the ramp, for the parabolic, and he got error signal, steady state error signal. Here was 0, 0, tau, and infinity. That's right, for the first order system. And we plotted in the Simulink, and I shared the Simulink file with you, and then we moved toward input of harmonic sine or cosine, but that we name it that frequency response. And I taught you how to plot Bode 20 log of y over x closed loop transfer function. And remember, when it comes to the MATLAB, I'm just writing here, please also you write there in your notes. When you want to code for control for responses, you have to put closed loop transfer function. Look at the step response, frequency response. When it comes to Simulink, as you see, and I'm sharing with you, you have to put open loop transfer function, remember? And I shared with you. And what we did for continuing that, so we just replaced SSJ omega as it is, tau plus 1, and we calculated A as 20 log, which is 1 over 1 plus tau square omega square. And we plotted this for different value of the frequency, excitation frequency, right? Sorry, excitation frequency. When we plotted that amplitude and we name it the Bode plot, when we plotted that in decibel, this A in decibel, as you saw in the MATLAB and Simulink I did in the last class. And here is the omega. You saw that this kind of first order system that can be RC circuit, tank of water, or the spring and damper in parallel is what we named it? You tell me. We named as what? Low pass filter, -3 decibel here was. And I set this frequency as cutoff frequency, cutoff frequency. Okay. Now I want to introduce you a new parameter. And this band, not this frequency, is it omega c here it is. This band, I'm pretty sure that you heard from your grandfather or your father when they were listening to radio, is bandwidth. Okay, bandwidth, like as we say that the bandwidth of 1090 in radio, okay, means that bandwidth that the output exactly is that is input. That's why you're gonna listen to the radio on that band, on that frequency, that bandwidth very clearly. But when you change the bandwidth out of the bandwidth, you're gonna have some noise because the output is smaller than input here. For example, okay, this is an example. So the bandwidth. So you see that because we said for this first order system, omega c was 1 over tau. Remember that we examined in the last class? Here was 1 over tau. You see, for this first order system or low pass filter, oh my god, this is because of COVID. I'm writing low as loss. This low pass filter, why low pass? Because only passing the low frequency. means that the y over x is 1. When this is 1, log of the 1 is 0. Here we go. Okay. So you see that there is a function of 1 over tau. What does it mean? It means if you reduce the tau, okay, what's gonna happen for you? Omega c gonna what? Increase. That's right. So this is, let me plot it for you. I'm gonna do in the MATLAB right now. If you increase the tau, for example, for the RC circuit, tau was, remember, was RC. Resistance in the capacitance, the values. So it's gonna be like this, say. This is when you increase tau. Sorry, decrease tau. But if you increase tau, the band, the cutoff frequency gonna decrease. That's right, based on this relation. So you're gonna have this. We're gonna examine now in the Simulink in MATLAB actually. So here we go. It's gonna be like that, for example. Okay, this is when tau increased. So you can decrease or increase or decrease the bandwidth of a signal. That's right, bandwidth. Even for the internet, so we say that the bandwidth is limited, or we have a limited bandwidth for the internet of university. This bandwidth is coming from here. You got it, everybody? Yes? Huh? So now let me show you in the MATLAB. So remember that I told you when you go to MATLAB coding, you have to write num as we did in the previous class. First order system here has no s, gonna be 0 and 1, and then here is, for example, tau. Tau is, I said, is 2. Remember in the previous class? Tau and 1, because tau is the first order system. So I'm gonna develop a code, a simple code. I'm gonna share with you. I'm gonna continue. Not in the Simulink today. A new MATLAB, new script. So I'm gonna CLC clear all. Always I do that, close all. This is the professional way of. So I say num is, don't worry, I'm gonna share this with you. It's gonna be 0 and 1, the closed loop transfer function. I'm writing here again. When you run it after graduation, you have this from me. For plotting responses, you have to write down closed loop transfer function. Okay, that Simulink must be open loop transfer function. Now and then, and now you know what? I'm gonna have tau 1. Tau 1. Tau 1 was 2 in the previous case. Tau 2. I'm gonna increase that to, I don't know, 6. And now I'm gonna this tau 3 gonna be 0.5. I want to see the effect here. So then one gonna be tau 1 and 1. I'm just copying and pasting. Then 2 tau 2 and 1, and then 3, because num we don't change it, 3. So then I'm gonna say figure 1, and I'm gonna say, you know, the command body num then. I'm not sure that this works, but I try. Let me first save this, because I'm gonna share with you. And this is body low pass filter different tau. So if I run this, oh, I have done one. Not done. Sorry guys. Okay, this is the original one we had the previous class. So tau is 2. This is that we had. I'm gonna derive this mathematically. Bear with me. I'm just talking about the amplitude magnitude. Okay, low pass filter, and this is the frequency. 10 to the power of minus 2, 10 to the power of minus 1, 1, and 10 radian per second. See that? Okay, now I'm gonna say hold on, as I did for you, and then two. Let me say this blue, and then 2 is increased. I'm gonna say red, and hold on, then 3 green, and grid. So here we go. As I told you, see that when it is minus 3, you see if I put a line here, okay, so the red, guys, red is for when I increased tau 2. I increase the time constant. So when I increase the time constant, I lower the bandwidth. Bandwidth is here, guys, for this. See here. For the original was bandwidth is here. For the green one, tau 3, that I decrease the tau. So I expect that the bandwidth increases. And here we go. See, I change the bandwidth by playing the time constant of the first order system, or here the low pass filter. You got it, everybody? Yes? Huh? Okay. So, oh, let me run it. Good. Bear with me. So also you see that the phase that I was talking, because the body has two components. One of this magnitude in decibel, another is phase degree, is decreasing from 0 to minus 90, okay, by the frequency changing. I'm going to talk about this, both of this, in Simulink and in MATLAB, okay? But first, let me derive it for you. We are still in the first order system. So I said, remember that the phase angle of this, that is phase angle of 1 over j omega tau plus 1. And I taught you in the previous class that this, if you look at your notes, mathematically, this is going to be the phase angle of 1 minus, because denominator, this is how we have it. A phase angle of j omega tau plus 1. Okay, guys, 1 means this. 1 plus 0s minus phase angle of j omega tau plus 1. So what's the phase angle of this? Look at here, guys. This is, nothing is accident. If I go to the phase plane, and here is 1. Suppose that you have this complex number. So phase of this, look at here, phase of this number means is tangent of phi. This is high school, not university. Say it is imaginary. It is imaginary in the complex plane, real, and this component is real. That's right. These are numbers. Tangent of phi is I over R. So the phase angle is tangent inverse of I over R. Means imaginary part over real part. You got it, everybody? Yes? You got it? Okay. So this is 1 plus 0 j omega, okay, minus j omega tau plus 1. You got it? So by doing that, if you give different numbers to the omega, you can calculate by calculator or in MATLAB. And it changes the phi from 0, okay, from 0 to minus 90 by here's the minus 90 degree, minus 90 degree. Here we go. This is omega, and this is the phase angle in degree, as you saw in the coding or in the simulator, in the coding of the MATLAB. Okay, so what does it mean, guys? What does this mean? Minus phi, minus 90. For the low pass filter, it says if you are in the low frequency, there is no phase angle. But if you increase that, eventually the phase angle is gonna be minus 90. Can you tell me what does it mean physically in real engineering? Hmm? Exactly. Exactly. Excellent job. Is lagging or leading to the original one, to the input to the system. Okay. So here can be written as, write it down, tangent inverse of imaginary part of this is 0 divided by 1, and tangent inverse of imaginary part is omega tau divided by 1. Tangent of 0 is 0, and here you have tangent, write it down everyone, in omega tau. So when omega is 0, let me examine to you. First let me derive it. When the omega is 0, or a small value, you get that phi gonna be 0, because 0, 0. When omega is equal to 1 over tau, or what? Here. Huh? Let me replot it, because this don't reflect reality, guys. Okay, so you get that phi gonna be minus tangent inverse of 1, which is minus 45 degree. Okay, actually here must be those. Sorry guys, the original ones was correct. Okay, here is minus 45. Oh my god, let me change the color, maybe this is not good. Say yeah, here, let me, yeah, here, say, okay. Actually, I'm going to show it in MATLAB, but okay. Here is at cutoff frequency is minus 45 degree. Huh? When the omega is large number, very large number, obviously phi gonna be minus tangent inverse of infinity, large number, which is 90, minus 90. And as your friend said, when you are increasing the frequency, you're gonna have what? Lead lag problem. Okay, I'm gonna show it physically now in the Simulink. You got everyone? This is what only first order system, okay, and low pass filter. I'm gonna continue right now. I'm not done yet. So let me open the Simulink file here and show you what we have. Open the model. You have it. I don't want to share it. I'm just gonna play with the numbers. Okay. Okay. Remember the code that you have, I mean the Simulink file you have. um, oh, where is do you remember the file name when I plotted this? Oh, first order. Sorry, I have to open this. Open model. Okay. So this is the harmonic input, sine, frequency response, and I keep this as 1/2, the time constant. I'm gonna play again with the frequency. Frequency, yeah, low frequency, guys. Remember? Come on. Here we go. In low frequency, there is no lead and lag. See, they are exactly on each other. So you see the peaks of those, they are at the same point. Okay? So that's why phase angle is 0. Okay? But when I increase the frequency based on the body, I'm increasing to 1 or 0.5, say. Hmm? I'll run it. Okay. Oh, here we go. So if I just magnify this part, you see, guys, this is the input, this is output. Okay. So the peaks is happening, you have delay. The phase angle here is delay. See what I'm saying? That negative phase angle means this, means happens after this. We don't like it. We are control engineer. We have to fix this. In addition to amplitude that is off, we have to fix it by phase margin and gain margin that I'm going to define. Okay. And if you increase the frequency to, I don't know, 3, much higher. And if you run it, phase angle goes to -90. Oh, it's too much. Forget about that. Okay. Okay, you saw it? So that negative phase angle here, here we go. That negative phase angle, -45, -90, means that you have what? You have a lag problem here. Your response happens with the phase shift with respect to the input. We don't like it. This is not a good control problem. We have to fix that. See what I'm saying, everybody? Huh? So you, later at the end of the semester, I'm gonna teach you about this, say 0.5 frequency. Here I'm going to say 50. Okay. Okay. Later you're going to see the blue line is the input and the output is this yellow line. Okay. You are off from the magnitude that we're going to call this the phase margin, simply speaking. Oh, sorry, gain margin. And you have a lag problem. It happens with this phase. Okay. And you have the phase margin. So you have to fix these two by the controller and back it here. You got the whole picture, everybody? Yes? So now I'm gonna close it for now. No. And now I will take you back to the notes because I taught you about the low pass filter, but as we are in the we are in the first order system. Why not teaching you high pass filter? High pass filter. Yes, yes. What again? Bias? Oh, yeah, yeah. Oh, let me run it. Okay, hold on. First order. Here you mean the code, you mean, that's right? Here? Oh, you mean the first order? Okay. Oh, where's that bias? I can't see it. Can you show me? Oh, you mean that the input. This is the phase angle. Okay. Like a sine omega t or sine omega t plus phi. That bias is phi. See what I'm saying? Okay. I said phase is here. Actually, let me see what's bias. So it's good. Hold on, because this bias is here, like sine omega t plus 3 plus number 2. Okay, so see what I'm saying? It means I know that you know it, but just for others, huh? So this is sine omega t. This is the numerical version of the MATLAB. Okay, so say I'm starting from here. This is the bias, say 2. You got it? Huh? So we don't want to do that because this is out of our topic. So So, so where we are. So let me close this. I won't work on that. And let me erase this. Yes, have it here. Okay. So high pass filter. You saw that the RC circuit or tank of water or say spring and damper from vibration I was teaching the previous class. In parallel, they are low pass filter, only passing the low frequency and with the band feed that you can change it with the time constant tau. Now, guys, look at this. If I change, even not change, the place of C and R and input voltage plus minus and I inside this, and this time instead of measuring the voltage of capacitor, I want to have this closed loop transfer function resistor. I want to calculate VR over Vin. The previous time in the first order system we had what? VC over Vin, capacitor. You got it, everybody? So if that's the case, again by the Kirchhoff voltage law, Vin is equal to VC plus VR. And here is VC, obviously. And remember that the VC is 1 over C into, I told you in the previous, I dt plus VR. This is from high school physics, not even university. But as we did, based on the Ohm law, VR is Ri. So from here we put I is equal to VR over R. Just gonna implement here inside here. If we do that, it's called the 1 over RC. Oh, the same term. VR dt plus VR. Now I want to go from time to frequency. You tell me what I have to do again. We are in control. What I have to do? Laplace. For refreshing your mind, you have your notes. Laplace of integration, I taught you, give you 1 over s. So we're gonna have v in s, gonna be 1 over rc integration s vrs plus vrs. You got it? When you see 1 over s means integrator, PID controller, I is for integrator, I taught you. When you see s means we have derivative, PID, d derivative. Okay? So this can be written as, from kindergarten level math, RCS plus 1 divided by RCS. So we get our closed loop transfer function as RCS plus 1. You got it? Now I named this as tau s over tau s plus 1. Here we go. What's the difference between this first order system, and previous one? I want to change the color. Only you're adding a 0 to the system. This is 0. These are poles of the system, roots of the numerator. Poles we defined. And the roots of the numerators are zeros. Zeros. So the pole of this system is 1 minus over tau. And z, we are showing with z. Zeros is 0. Because s is equal to 0. Here we go, from kindergarten. So if you want to show it in the complex plane for this first order system, real imaginary, I told you we are showing poles by cross, one pole, and we are showing, this is a standard convention, zeros by circle. We have a 0 at the origin, here 0. You got it? And we name this system as high pass filter. High pass filter. Okay. How? Pretty simple, guys. Just again, we're gonna put a is 20 log of y over x. We know that the y over x we just derived is j omega tau over j omega tau plus 1. We replaced s with j omega. That's the main difference. See, here was only 1 plus j omega tau. Here you have that plus another 1 here. So we're gonna have 20 log of what? Omega tau 1 plus omega tau square. Here we go. Now you have to give different values of the omega, okay, and plot it. The same for phase. First, let me write for phase. I'm sorry, guys. So the phase angle of this gonna be phase angle of j omega tau minus phase angle of j omega tau plus 1. So guys, what's the phase angle of this from high school? Means tangent, as I taught you today, inverse of imaginary over real. There has no real. Its real part is 0. It's like this. Minus tangent inverse of imaginary. How much is this from elementary school? Mathematically. Any number divided by 0. Infinity. Which angle tangent is infinity? 90 minus tangent inverse of omega tau. Change different values to omega and plot it. And this is for the amplitude. So to avoid that ridiculous trivial steps, I'm taking you exactly to coding because I'm going to share with you. Not you now. Where is the code? Okay. First, I have to change it low and high pass. I have to change this before sending to you. Okay. So now we have a difference. Num1, 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 num1. Now I'm gonna go to the second part. I'm gonna say num2 because num changed, guys. Your num is tau s. So if you want to write it in MATLAB coding, closed transfer function gonna be num gonna be tau and 0. See, only tau and 0. And your den is the same, tau and 1. See, here num changed. You got it, everybody? Yes? Tell me yes. Good. So num is tau, what we define here? Tau 1. Just 2 seconds, huh? Here we go. Oh, I'm sorry, guys. See, difference between 0 and 1. Okay. Now it's changed to tau 1 and 0. See, changed. And I have den 1. We don't need that because den 1 is the same. So I'm going to say figure 2 body and num2 and den 1 and grid for me. Okay. And let me change the color for this blue. Okay, tau 1 on this. Oh, interesting, guys. Look at, I'm comparing these together, guys. For low pass filter, we are passing on low frequencies. Y over X was 1. Means that the output follows the input. High frequency, the amplitude of the output was decreasing, as I showed physically in the Simulink. In high pass filter, we are only passing high frequencies. See here? Y over X is 1, so logarithm of that is 0. Here we go. For low frequencies, the output amplitude decreases. You see here? You got the difference, everyone? Yes? Huh? Yes, everybody? Huh? Yes. Good. Yeah, you have a question? So the phase angle of the low pass filter that can be tank of water as first order system was starting from 0 to minus 90. Phase angle of the high pass filter is starting from 90 to 0. Why? Because from kindergarten we did this. 90 minus, if omega is 0, this is 0, gonna be 90. Is omega is 1 over tau gonna be 1, 45, 45. If omega is infinity, large number gonna be 90 minus 90 is how much, for God's sake? 0. Here we go, 0. So this is high pass filter and low pass filter. Now you know after graduation of this course, when you're talking about any frequency domain and I'm gonna use high pass filter, low pass filter. Okay, you know how they work. High pass filter passing only the high frequencies, low pass filter only passing sorry, high frequencies, low pass filter has only low frequencies. You got it? Now, if I want to go and see its effect in reality, let me go back here. I said I want to go to Simulink high pass filter. Y over X was tau S plus 1. But in Simulink, what we have to use? You tell me. Open loop or closed loop in Simulink? Open loop, G. So this equals to tau S plus 1 based on the unity feedback is G1 plus G. We have to find G from here. Let's do that. Okay. So it's going to be tau S 1 plus G and G tau S plus 1. It's going to be tau S plus tau S G, and this is G tau S plus 1. If you move to the other side, you get tau S, and here you get what? G. Everyone agree? Yes? Here we go. You have to implement this in the Simulink, guys. You got it? Huh? Understand, everybody? Good. Okay, how to do that? I taught you. Because we don't have derivative in Simulink. So you have to write like this, guys. Tau S plus 0, a transfer function. Here you have to put, say, 0.1 S plus 1. This is compared to is very small, so it is vanishing. You got it, everybody? So if I go to Simulink, I'm going to share with you again. Okay. You know what? I'm going to put to the new one, compare the low pass filter with high pass filter. New blank model. Not now. Okay. And now I'm gonna copy and paste. Okay, this was, I'm writing here for transfer function of, I'm writing here. Okay. What the hell is this? Okay. This is transfer function of, actually open loop. Transfer function of low pass filter. And this is open loop transfer function of high pass filter. So now we have to change it, as I told you. So it's tau S, tau is 2, right? And 0, exactly, I'm copying from here, guys. Tau is plus 0, tau, and a small value and 1. So it gives you this small value and 1. This is going to be tau S. Right, here we go. And now frequency. Okay, guys, let us examine these figures both together. I want to see, I'm going to show the both of to you. Okay. First, I'm going to examine low frequency for both. Low frequency, I said here is 0.01. Remember? And the same is low frequency. And if let me change it as comparison of low and high pass filter. Okay. And let me give you an and. Now I will have to put it as 800 because low pass frequency, and I'm gonna run it. You saw that for the low pass filter, they were exactly the same, right? On each other, for low frequency. For a high pass filter, oh my God, see the offset and the phase. Phase is plus 90 here, remember? Plus 90 means we have lead problem, see? See the peak of this and peak of this? It's leading the input. As your friend said, plus 90 means leading. Minus that we had means lagging. See? See, guys? So on the other hand, if I want to plot together for a comparison, oh man, I'm gonna, you can double check on, double click on marks and say 3 inputs. Okay, now I'm gonna compare this low pass filter by high pass filter with the same signal. Okay, input. Look at here, guys. That's the difference. Here we go. This green line and the yellow line is for the low pass filter, and the red line is for the high pass filter. So that plus 90, here we go. Plus 90 means we have a lead problem. And amplitude obviously reduced, a lot reduced. You see what I'm saying, everybody? Now let us increase the frequency. Frequency to 0.1. Tau is 2. Let me add 0.1 is good. And 10 times. 0.1. Okay. And now I'm comparing everything. Good, guys. So still the red, what? The red is the low pass filter, a high pass filter. This is, we have the less off from the amplitude, and we have what? We have what? Lag from the phase for low pass filter. We have lead for high pass filter still. And if I increase more the frequency, going to half high frequency, let me say 0.6. Point 6. And reduce this to 300 seconds. Here we go. Okay, guys. The green is input. The red now is getting close to the input because we are going to high frequency. Look at here. We are going here almost. The yellow is what? Is a low pass filter, is offset. But still we have lead of the high pass filter because of plus 90 going to 0, and we have lag of the low pass filter. It's happening after that. Now if I increase more, going to 1 radian per second. 1. I have to go to 100 seconds. Okay. See? They are getting close. See? They are getting close sometimes. Okay? But low pass filter is going down. going down. But I have to increase the sample time. Here we go. See that red and green, they are now almost the same at amplitude and almost at the phase, but the low pass filter decreased a lot, see, in the high frequency. You got it, everybody? Yes? So I'm going to share this code with you and this code with you, but I have to change its name. I have to say it, where's his name? Okay, comparison. So we did this. We have also, what is that? Oh, here we go. Body, low, and a high pass filter. Okay, here we go. I changed the name when I'm sharing with you. Now, guys, I'm almost done with the first order system and the body plot of that. And now you're familiar with the phase and amplitude and the phase margin and gain margin physically that you're going to see at the end of the semester. To using the controller to compensate for that, the phase margin and gain margin you saw physically. Now for yourself at home, if your closed transfer function is S, means derivative, or if your transfer function is 1 over S, means integrator, and if your closed transfer function is this 1 plus 2S, you have 1, 0. Plot their body by hand, as I did. Replace Sj omega, do the condition of that, and plot it, and validate by MATLAB coding. MATLAB for yourself as homework. See if you can validate in MATLAB. Okay? You got it? Everybody? So I want to just recap what I taught you. The first order system in the format of the low pass filter, like a tank of water, RC circuit, and spring and damper in series. You have one pole, a stable pole. This is pole. We are showing with cross on the left hand side. For high pass filter or CR circuit, that's why I changed the place, that I can name it properly. Or CR system, we had a 0 at the origin and a pole. High pass filter as a first order system. I'm sorry. High pass filter as the first order system, and I'm getting older, guys. And the low pass filter as a first order system. This was 1 over tau s plus 1 y over x closed transfer function. This was, we added a 0, tau s plus 1. And both are stable. When I teach you root locus, you're going to see that the poles of the system always move toward the zeros of the system. Not now. After teaching you PID, I'm going to teach you root locus in MATLAB in theory. You see that always system goes from the poles to 0. It has a physical reason. I'm going to teach you. Next class, we're going to start second order systems. And your classmate that asked about that for the robotic system, can we have the underdamped response? And I said no. Eventually I'm going to answer this here. Okay. And in second order system, after we plotting different scenarios and deriving, I have to teach you the body of the second order system. Okay. Okay, so let's